So the first thing that we're going to deal with series of non-negative terms is a claim that a series with non-negative terms always has a sum. That is, it can't not have a sum, and that sum is either going to be finite or infinite. So let's deal with that. So first off, we're going to just let a sub n be, or the sum of a sub n's be a series with non-negative terms. So that is to say each term a sub n is greater than or equal to 0, and the sequence of partial sums are going to satisfy this. And so the first partial sum is just the first term, and then the second partial sum is the first term plus the second term. And since a sub 2 has to be greater than or equal to 0, well then remember this is actually just the first partial sum plus the second term, and a sub 2 is greater than or equal to 0, so this actually has to be greater than or equal to the first partial sum. On the third partial sum, it's the first three terms added together. Well, a1 plus a2, that's s2, right? That's s sub 2. So that's really the second partial sum plus the third term, and that has to be, because this third term, a sub 3 is greater than or equal to 0, that means that this is greater than or equal to the second partial sum. And this idea keeps going until I get down to the nth term, and the nth term is equal to the nth partial sum is equal to the n minus 1 partial sum plus the nth term, and that has to be greater than or equal to the previous partial sum, because again this a sub n is greater than or equal to 0. And so what I can say in general is that my sequence is increasing. This is s sub 1 right here, s sub 1, s sub 2, s sub 3, all the way to s sub n, and keep on going and going and going. So then what can I say from here? Well, one of two things is happening, right? I have this sequence here, pardon my board etiquette, and notice that this is a monotone sequence because it's increasing, and one of two things is happening. Either it's bounded above or it's not. So if the sequence is bounded above, well then I have a monotone bounded sequence, and I know that that then means that it has to converge. We have a theorem about that monotone bounded sequences do in fact converge. Remember, the partial sums themselves are a sequence. So I'm going back to this idea of sequences. A bounded monotone sequence does converge, right? There exists, this backwards e is, there exists an m such that for every s sub n, it's less than or equal to some big M, and then this says, then because of that, then that means that the limit of the partial sums has to be some s, which is less than or equal to m. Now remember, I don't have to pick the smallest bound, I just have to pick a bound. So that m could be s, but that m could also be something way bigger than s. Like if you're like, oh, it's bounded by 1,000,000, that would be fine as long as you can show it's bounded by at least 1,000,000. You're just looking for an upper bound, not the least upper bound. So it's either bounded. If it's not bounded, so if it's bounded, it converges and it has a finite sum. If it's not bounded, and when I'm saying it, I'm referring to the sequence of partial sums. Every time I say it, the it in this case is my sequence. Oh, and I'm reading off board, I'm sorry. Is in fact my, I can't get off camera, or can't get on camera, is my sequence of partial sums. This is a that. I went too far off camera, sorry guys. Trying to figure out where the camera is. And you can't see the T. That word is that, such that. So if it's not bounded, then then this sequence can get arbitrarily large. And if it can get arbitrarily large, then its sum is infinite. So the sum is infinite. And this idea is going to help us when we're dealing with our series with non-negative terms. So again, what have we shown? We've shown the top, that a series with non-negative terms, that is a series that looks like this, that looks like a sub n with each term greater than or equal to 0, it either has a finite or an infinite sum.